Alright, welcome to the first official physics video that has physics content. This is going to be chapter 4 in the textbook, which is all about forces, and we're going to go through it relatively quickly with the idea that you can pause if you need to catch up on taking notes, and that you can rewatch sections if it's not clear. But that way, if you just want to go through the content, you can make it through relatively quickly. Please make sure you've got paper and pencil out in front of you and you're taking notes just as if this were an in-class lecture. Alright, here we go. Okay, so welcome, chapter 4, get ready to go. Force, what comes to mind? So, I'm sure you've heard this word before, we all have, and what you think about when you hear the word force, or when you think about forces, some of you guys probably have ideas about it that match up with what we're going to talk about in physics class, and some of you probably have ideas about things that are forces in your daily lives that are not actual forces by the physics definition. So we'll kind of elucidate what those mean. This is more of a classroom discussion that we'll have once we get to class. Alright, two fun pictures. When you hear the word force, you might think of a gunshot as exerting a force. You might think of getting hit in the face with a soccer ball as exerting a force. And both of those are examples of forces, but only for part of the whole experience. So what I mean by that is when the bullet is inside of the gun and you pull the trigger and the bullet is launched out of the gun, during the time that the bullet is being launched, there's a force exerted on it. But once the bullet leaves the gun, actually there's no longer a physics force exerted on it. So when the bullet is just flying through the air, there's no force being exerted on it by the gun. And we'll, that's just one example. We'll go into a lot of detail throughout the chapter. Alright. Same as a soccer ball hitting someone in the face. On its way to you and after it's left you, it is not exerting a force, but while the two are in contact, it is exerting a force. When and where can they happen? What can experience a force? What can cause a force? All of these are questions we'll discuss in class as a group. So here are the topics. That was just a mental introduction to force. Here are the topics that we're going to be covering. We might have to break it into a couple of videos if it starts to take too long, but we'll go through them a little bit at a time. So we'll first talk about their relation to motion and how they come in vector pairs. So we've already spent about a week and a half talking about motion. Chapter 2 was simple motion, where it was just constant velocity, nothing was changing speed, and our formula was like velocity is distance over time. Then last week in chapter 3 we learned about accelerated motion, so things were allowed to be speeding up and slowing down, and you saw that there was a lot that made it a lot more complicated, and we had 4 different equations that we could use because there were 5 variables. There's initial velocity, final velocity, distance, time, and acceleration. And because there's 5 unknowns, we have to have 4 equations so we can solve for whichever one we're missing. So we've seen all of this motion, speeding up, slowing down, and now we're going to learn what actually causes it to happen. So if something is accelerating, well, why is it accelerating? What's causing it to accelerate? What forces are needed to do that? All right, and as I've said here, this is the biggest topic of the semester. So forces in general and all of their applications are the most important thing you're going to learn in the first semester. So number one, and easy to forget, but very, very important, is that forces come in pairs. So what that means is you can't have a force of, say, let me just talk about kicking a soccer ball. When my foot hits a soccer ball, there's a force from my foot on the soccer ball. But there's also a force from the soccer ball on my foot. It comes as a pair between the two objects, and it's impossible to have one without the other. So a force is any push or pull from one object on another. You can't have a force if there's only one object. We're going to use the capital F as our symbol for force, and the units are going to be newtons, which is capital N. Again, there must be 2 objects. One is pushing or pulling, and one is being pushed or being pulled. And sometimes it's very difficult to distinguish between the pusher and the pushee. And it doesn't matter. Like, there's no effect whatsoever. Okay. Here's another example. Take a textbook and hold it up, and then punch it with your hand, and see what happens. And then hold your fist steady, and then crash the textbook into your hand. And you can see that in both cases, there's an interaction between the book and your hand. But whether it's your hand moving into the book, or whether it's the book moving into your hand, how it feels to you shouldn't be different. So there's an example. And finally, notice that it is a vector, which means that the direction matters. So a force north is different than a force south. Just like when we had cars driving on the freeway, their velocity was a vector, their acceleration was a vector, so direction matters. Same as force, because force is going to cause motion. If I say there's a force of 10 newtons, but I don't tell you which direction it was pushing, it's going to be pretty difficult for you to figure out which way the object is going to move, because it depends which way you pushed it. Okay, force diagrams. This is the picture that you're going to draw, which will enable you to solve the problem. And if you have a force diagram accurately labeled and drawn well, there's a really, really high chance you're going to get the problem correct. And if you have your force diagram incorrect or incomplete, there's almost no chance you're going to get it right. So this is absolutely very, very important. So basically every problem in this chapter you're going to need to draw a force diagram for. So treat it as a requirement. You're going to draw the object as a small circle or box. Every single force that's acting on that object is going to be represented by an arrow in your picture that starts on the object and then points in the direction of the force. And finally, the length of the arrow will be representing the size of the force. So a bigger force will require a bigger arrow. And then you need to label all of the arrows with what the force is, the force name. So here's going to be a lot of examples. These aren't going to make sense because we haven't learned about all these forces yet, but just get the idea of what it's going to look like. So you've got a box. Okay, this box right now has 4 forces acting on it. They're all labeled and they all have arrows. So what's the smallest one? Force of frict, which is going to actually be friction, which we'll learn about very soon. That one is going to be the smallest one. You can tell because the arrow is shorter than the other arrows and it's pointing to the left. FAPP, that stands for the force applied. So for example, if you're pushing it, Fgrav is the force of gravity downward, and Fnorm is called a normal force, and that points upward. And again, we'll go through all the specific types of force. This is just to give you an idea of what a force diagram might look like. Here's another one for a box sitting on an inclined plane. You've got the force of the earth on the block. Okay, that's another way of writing the force of gravity on the block. The force of the plane on the block is capital N. They use capital N instead of writing F norm. So this is just different notation. I got these pictures from the internet. And then F plane on block is the force parallel to the plane. So, you know, I'll talk about it in class, and maybe on the next slide I'll give some more examples of how I want you guys to draw force diagrams. Here's another one, someone's pushing it. So if they push it, there's a force forward, FA for F applied, force of gravity down, force normal up. And then this little A right here, this is absolutely not part of the force diagram. This is just a separate little arrow showing that the acceleration will be in this direction. So it's not coming out of the object. So it's not a force. It also doesn't have a capital F, obviously. All right. Okay, so now let's look at the specific type of forces that you're going to be putting onto your force diagrams. There's 2 categories which all the forces are going to fall into. One of them is contact and one of them is long range. I think the titles are pretty self-explanatory, and I've got pictures to make it even more obvious. So when 2 interacting objects touch each other, then there's a force between them called a contact force. So this picture is nice. It's a baseball bat hitting a baseball. Obviously, if you swing and you miss the baseball, you're not going to be able to exert a force and accelerate it, you know, for home run or whatever. Like, there has to be physical contact between these 2 objects for there to be a force from the bat on the ball or the ball on the bat. This is a good example for me to illustrate that the forces come in pairs. Any of you have ever hit a ball with a baseball bat? You know that the bat hits the ball, and there's a force on the ball which launches it. But if you've actually held the baseball bat, you definitely feel the force from the ball on the bat, and it makes it vibrate, and sometimes it hurts your hands if you're not holding it properly. So there's definitely an equal and opposite force from the ball on the bat as whatever the bat is doing to the ball. Okay. The other type of force is called long range. So, you know, usually 99% of the time, any force that's exerted on an object is because of something touching it. But there are a couple examples, just a few, of forces on objects from something far away that's not touching it. And so that's called a long range force. In this picture, you see these bombs dropping out. What force is causing these bombs to fall? Well, I'm sure you guys all know it's gravity. So for the first semester, actually, gravity is the only long-range force that we'll learn about. Then in second semester, we'll learn about electricity and magnetism, which are also long-range forces. But as far as first semester goes, when you're drawing your force diagram, you've got gravity as your long-range force, and then anything that's touching your object as your contact forces, and that's it. So it shouldn't be too difficult to remember or to figure out which forces are on a given diagram. It's gravity for long range, and things that are touching it for contact. If it's not touching it, it's not exerting a force on it. Okay, let's talk about gravity a little bit more. In the textbook, it actually doesn't talk about gravity until, I think it's chapter 7, but because it's such an important force in all force diagrams, I want to take some special time to devote to it right now. So it's a basic and fundamental force. If you ask me, oh Morgan, why is there gravity? Like, I can't really tell you. I don't have a good answer for that. It's the way that the world works. You can be religious and say it's because of God. You can be scientific and say it's just the law of nature, how it is, whatever. So don't dwell on that unless you want to chat me up in office hours or something. I'm happy to talk about the abstract philosophy of why gravity exists. But for the purposes of physics class, we know it exists. We've got experimental evidence, and so we just have to roll with it. Okay, so the result is that every object attracts every other object by a force called gravity, and it depends on how close the objects are, and it depends on how big the objects are. So this equation right here, let's get the mouse going, F sub g stands for the force of gravity, equals capital G. This is a constant of proportionality. And then force of gravity is directly proportional to the mass of the first object, directly proportional to the mass of the second object, and inverse quadratic, or inverse squared, proportional to distance. Remember those mathematical relationships we were talking about. So what that means is if you double the mass of one object, you double the force of gravity. If you double the mass of the other object, you double the force of gravity. But if you move them twice as far away, the force of gravity gets reduced because it's in the denominator, but it doesn't just get cut in half, it actually gets cut by a factor of 4 because it's r squared. So r squared means inverse square, and if you move things farther away, the force of gravity decreases proportional to the square, which means if you move them far away, the force gets small very, very quickly. So the masses should be in kilograms, and the distance here, r, should be in meters, and then your force will come out in newtons, because the standard units for this constant of proportionality are newtons, meters, and kilograms. And the value of this capital G is a very small number, 6.67 times 10 to the negative 11th. So what that's telling you is the force of gravity is going to be really, really small in all cases, except where the masses involved are super, super large, or the distance between the two objects is super, super small. So you're only going to have gravitational effects between super large objects, aka like the sun and the earth, or if things are really, really, really close together. But for the most part, gravity affects big things. It's what holds you to the earth, but the earth is really big. How about what holds you to the person sitting next to you? You're attracted to whoever's sitting next to you, but the force, because the two objects are both very small masses, the force is really, really, really tiny, and you can't really tell. So this equation is called the universal law of gravity, and it's the force that attracts every object to every other object. Okay, so what about on Earth's surface? Things do attract to each other, but it's not like when you drop a penny down a skyscraper, it arcs in and hits the building because the force of gravity between the penny and the building is so large. No, that never happens. So what's going on Earth's surface? So what I want to do is maybe I'll get a blank slide and show you some calculations. There's a lot of other forces also present. So the effect of the motion is what's happening overall. You have to take all the forces into consideration, not just look at one of them by itself. And the second thing is, and the more important thing is, the Earth is so big compared to everything else that you can pretty much ignore it. It's kind of like, if you're a billionaire and someone throws you 10 cents, you're not even going to notice. So when you're looking at the forces on an object, yes, there's a force attracting the penny to the skyscraper, but the force that's attracting it straight down is so much larger by comparison, that sideways force is negligible. You can ignore it. It's so small, it's insignificant. So what is the force of gravity affecting us on Earth's surface, and why do we get pulled straight down? This slide is going to explain it in glorious detail, and it says math to be worked out on the board, so I'll just make a blank slide on here and do it. We can simplify the universal gravity equation as follows. All right. Our objective is to get just the force of gravity on Earth's surface. So let me insert a slide here. A new slide. Okay, Shift F5. Let's get a little pen going. Okay, so we had that the force of gravity equals capital G m1 m2 over r squared. Now, let's think about on Earth's surface, which of these are variables and which of these are numbers, okay? Capital G is constant. So no matter what two objects you have, that's always the same. Okay, now if we're just looking on Earth's surface, what about the other one? I think Earth's might be capitalized, I don't know. Earth's surface. What do we know? Okay, the radius, does it really matter if you climb 10 feet up to the second floor or onto your roof? The radius of the Earth is around 6,380 kilometers, okay? If you add 10 feet to that, it's so insignificant that you can ignore it. So we're going to treat the radius of the Earth as constant, and the radius of the Earth is 6,000, approximately 380 kilometers, which is 6,380,000 meters, okay? How about the mass of the Earth? The mass of the Earth is also not changing. It doesn't matter where you go or which object you pick up, the mass of the Earth is constant. And you know what, to be perfectly honest, I cannot remember it off the top of my head. So look it up. In fact, I'm going to look it up right now. And I'm going to teach you how to be resourceful. Oh crap. Keep. You go onto the internet and you go here and then you type in google.com and then you type in mass of the Earth and holy crap, there it is. 5.972. Let's just round that to 6. The little e means times 10 to the power of 24th. Oh, it's better. It's better right here. 5.97, so 6 times 10 to the 24th kilograms. Okay, back to our slide. So we've got 6 times 10 to the 24th kilograms. Okay. Oh, that's mass 1, by the way. Sorry. Let me get back to blue here. Okay. Mass 2 is depends on the object, right? So if you're looking at the force of gravity on you, it's the mass of you. If you're looking at the force of gravity on an apple, it's the mass of the apple. So we want to say this depends, sorry, my handwriting is crappy, depends on the object. Okay, so what we're going to do now, what you're going to do, take out your calculator, plug in, let's get one more time, new color, let's go with orange. Plug this number in, right here, make sure you square it, okay? Plug this number in, right here, and do you remember the value of G? That was 6.67 times 10 to the negative 11th, and the units are Newton meters squared per kilogram squared. Doesn't matter that much. So take that number and plug it in there. Okay, and what you're going to get is M2, because M2 is still M2, times some number. Now I want you to maybe pause the video, type all that stuff in your calculator, and when you unpause the video, this is what you should get. You should get 9.8, and the units you should get out are 9.8 newtons per kilogram. Newtons per kilogram, okay. And that number, you know, you have to round it to get 9.8. It's like 9.7 or something like that. 9.75, I don't know what it is. But we're rounding it to 9.8 because that's the average on Earth's surface, taking into consideration different fluctuations in the radius, different fluctuations in the mass. Like, these are rounded values. But this 9.8 you should recognize from before. That was the acceleration due to gravity, okay? And so instead of calling it 9.8, we just call it G because that's much easier to write. And now we don't have to subscript M2 because now there's only one M in the formula. We don't have to do M2. We can just do mg. So the result of this is that the force of gravity on Earth's surface, I can't emphasize how important this is. On Earth's surface, the force of gravity is equal to mg. Now, what if you're not on Earth's surface? Well, shit, then you better not use this formula. It's only valid on Earth's surface, nowhere else. Because we plugged in specific values, the radius of the Earth, the mass of the Earth. So it's only valid on Earth. But 99% of what we're doing in this class, you know, experiments, the physics of the daily world, are happening at the Earth's surface. So it's very helpful, and that's what we want to typically do. Okay. So let's get back to it. Let's talk about another type of force called the normal force. So when two objects touch, there's a force preventing them from overlapping. So when I set something on the table, right? Set a book on the table, set your pencil down on the table. It doesn't fall through. Why not? Well, there's a downward force on the pencil of gravity pulling it down, but the table is supporting it, which has to cause an upward force to prevent the pencil from falling. So the force from the table on the pencil is perpendicular to the surface, and mathematically the word normal, F normal here, normal force means perpendicular. So it's always perpendicular to the surface. If your surface is perfectly flat, the normal force will point straight upward. Later on we'll see that if you have a surface at an incline, the normal force will point at an angle upward. So normal force is going to be capital F for force, and a subscript normal, or just an N. Let's pause here and break this video into multiple parts. When we come back, we'll talk about the concept of F net.